Swayam Prabha. Digital India. Educated India.
So, in the last class we had established equivalence between the electrical side and the mechanical side. So, we had mapped velocity onto voltage, force onto current, compliance which is inverse of stiffness onto inductance, and the moving mass of an object onto capacitance, and then we introduced a term which is inverse of damping called mechanical resistance, and that we mapped to the electrical resistance. As we developed this analogy, we had seen that we had mapped u, which is the velocity, to voltage. One thing in this context it may be important to understand is that if I draw a circuit, it could be any circuit. I have a voltage source and there is an impedance, there is another impedance, and then I am closing the circuit. So, here the impedance is Z1, here the impedance is Z2. It is actually physically possible for me to measure the voltage across this impedance by using a voltmeter, and in doing so I do not have to cut the cable here. If I have to measure the current, then I have to introduce an ammeter here, and then I have to actually physically cut the circuit. Now, there are newer current measuring devices which use magnetic fields, but some of the less expensive ways is that you have to cut the thing and then measure current going through that circuit. Similarly, when I have to measure this velocity, I do not have to break the mechanical circuit. If something is moving, I can use a laser or some displacement meter to measure the velocity. If I have to measure force, which is analogous to current, I have to again break the circuit, because force is something which passes through the stream of things, and then so it is important to understand that. And that is another benefit of this analogy which we are using. So, this analogy where we had equated u with, not equated, we had established analogy between u and voltage and force and current and so on and so forth, is called mobility analogy. It is also called inverse analogy. There is another set of analogies which is called direct analogy or impedance analogy, where these mappings are just the opposite. So, we will very quickly go over that. So, what we are going to talk about is direct or impedance analogy. So, we will start very quickly with a dashpot. So, force equals C x dot, which gives me force equals C times u, which is velocity, which gives me force equals Rm times u. So, here it is in uppercase. So, Rm is same as the damping coefficient. So, from this I can say force equals Rm times u, and we will see that. And if I say that force is similar to voltage, u is similar to current, and my element variable, which is Rm or damping coefficient, Rm is similar to electrical resistance. So, this is for dashpot. I see that it's direct, it's called direct probably, because you have force which is mapping onto voltage, where volt is itself like a force type of a quantity. It relates to electromagnetic EMF, electromotive force. It's I have no clear answer for that question, but this is a terminology and we are just using it. But I don't know exactly the history behind the nomenclature. So the other one is spring. So force equals stiffness times displacement is equivalent to force equals stiffness times integral of u dt. So it is same as force equals 1 over Cm times integral of u dt, where Cm is my capacitance, compliance. So again, force maps to voltage, velocity maps to current, and my compliance maps to capacitance. And then I go to mass, and here force equals mass times acceleration, that is force equals mass times first derivative of velocity over in time. So I mean, we had earlier used mm, that is moving mass. So I'll just use the same notation, and I know that in electrical area voltage equals L di over dt. So again, my force looks similar to voltage, I looks similar to velocity, looks similar to current, and my moving mass mm looks similar to inductance. So this is my other analogy. Now if I do a 4-point transformer in this, you will see that the turn ratio instead of T is to 1 comes as 1 is to T. So we will do couple of examples where we will just construct mechanical circuits, not electromechanical circuits, just mechanical circuits, and so that we develop some practice. Let us say I have a spring mass and a damper system like this. So I have a spring and also I have a dashpot. This is connected to a moving mass acted upon a force due to gravity. So it is mm, the force on it is mm times g, which is an external force, and let us say I am exciting at this end us. Here it is mechanical resistance is lowercase rm, and the compliance of this is Cm. So if I have to construct a equivalent electrical circuit, then what I will do is I have a voltage source which is us, so then also I have a moving mass mm, and in some of the earlier lectures we had said that moving mass always refers to an inertial frame, which in electrical engineering translates to a ground line, which is this. So I put a capacitance of value mm, then I have to ground it, which is my reference, and then the mass is connected in parallel to a spring and a dashpot. So I have a resistance of value Rm, and I have a inductor which mimics the performance of a spring, and the value is Cm. So I am missing one thing in this picture. What is that? So I have also gravity. I have to put, and the gravity is acting on the mass, and that current flows through dashpot and also the spring. So I can put a current source also here, and the value of that is mm times g, like that. So in this case, what I can do is, initially when the thing is set up and it's having no excitation of us, then I can solve using this current source of mm times g, and basically that will give me a DC offset in the whole displacement and velocity, right? And then once I have that, velocity will be 0 because it is a quasi static situation, but there will be, the mass will move down a little bit, then after some time it will stabilize. I can figure out what is the displacement of that, then I apply an external voltage and then again solve it. So whatever my total displacement will be, initial displacement, which is a consequence of gravity, plus the displacement due to this excitation velocity. So that is how I can solve it. So what you are seeing here is that instead of writing long equations, if I am able to develop a lumped system for lumped mass system for this entire mechanical network, then fairly in a very straightforward way I can solve for complex systems. This is a simple system, but I can also solve for complex systems. So we'll do a couple of more examples. Let's look at another one where I'm having two masses. So I have a base, I have a piston, let's say a cylinder and a piston. And inside this I have a piston. The mass of piston is mm1. The mass of the cylinder is mm2. Also, I am exciting my piston by a velocity source u1. It could be this could be driven by a motor, and the piston could go back and forth. Then I have a rigid frame in which this cylinder is, on which this cylinder is placed, and I have a spring. So I have a rigid frame and there's a spring of compliance Cm. The friction between the piston and the cylinder could be, we designate it as Rm1, and the friction between the cylinder and the frame on this surface is Rm2, and this is ground plane. So this is rigidly held. So if I have to develop a circuit for this, again I have a velocity source which is like a voltage source, generating velocity of u1. How many masses do I have in this? Two masses, mm1 and mm2. So I have two masses, and I am using mobility analogy. So this is mm1, mm2, and I have to again ground the masses. Because I have to provide an inertial frame to them. Then my first mass is linked to the second mass through this, and the interface between that I have mechanical resistance Rm1. Of course, the first mass is also seeing excitation through u1, and the second mass and the ground are connected in parallel through two elements, Cm and the resistance. So I have an inductance of value Cm, and then I have another resistance, mechanical resistance, value Rm1. Because whatever force which is being exerted by the second mass will be distributed amongst the compliance member and the friction member. So they are in parallel. The force will split into F1 and F2, two things, through those two members, right? So you have to, like what Mayank asked, you have to think a little bit carefully how I have to construct those elements. But once you have the circuit network correct, then it's fairly straightforward to solve these problems. We'll do one more example and then we'll move on. And in this case, what we will do is the example of an automobile suspension. So typically you have a car, 4 wheels. On each wheel you have a spring and also a dashpot, a damper to kill the vibrations. And then on that structure you have the mass of the whole car distributed, right? So if I just take one wheel plus one dashpot plus one stiffness member, then that system will see 1/4 of the mass of the car. I have ground, then I have a wheel. Wheel could have a mass, let's call it mm, and of course there's air inside the wheel also, so it is acting as also spring. So I have Cm. Then the wheel is connected to a dashpot and also it is connected to a spring. So let's call the spring stiffness to be Cms and the damper resistance to be Rms. So I have two springs in this case. One spring is inbuilt into the wheel itself by its very structure. You can also argue that wheel also has some damping properties because it's made of rubber and all that. You can also incorporate that, but typically the damping provided by the wheel itself is not significant, so we can drop it. And then on top of it, what do I have? The mass of the car. How much mass? 1/4. So I put a mass here and I call it mm of car. What am I interested in when I am doing this? That if I have any disturbance in the vertical direction, in this direction, coming from the road, suppose the car is going like that and you have a bump on the road, so it will induce a velocity of uw, right, or u road you can call it. And then what am I interested in? That the person who is sitting here in this MMC, how much of a velocity he sees. Ideally, you would like that value is 0, right? That is the ideal situation. So what you are interested in knowing is what is u car. So is everyone clear about these terminologies? MMC is mass of the car, 1/4. U car is velocity of the car where the passenger is sitting. CMS is compliance of the suspension stiffness. RMS is damping, mechanical resistance of the damper. MM and CM are the wheel of the mass and compliance of the mass. So we will construct a mechanical circuit for this. So again, this is my excitation, which is acting like a voltage source. So I call it UR. And then I have two masses. The first mass is the mass of the wheel. So I make it M W. I will connect it to ground. The second mass is mass of the car, MC, and again ground it. There is a stiffness member between this mass and the excitation source, which is Cm. W. Okay. You could ask, why is this CMW not in parallel to this mass? So any thoughts on that? The compliance in the wheel, why is it not in parallel to the mass of the wheel itself? For that you have to see the physics of the problem.
It's between the road and the.
So where is mass of the wheel? Most of the mass of the wheel is concentrated at the center where you have iron or steel, and between that steel and the road you have that air getting compressed. So it's not in parallel, it isn't series. So from here I have two mechanical elements in parallel, CMS, and then these guys are connected to. So this value is CMS and this value is RMS. What I am interested to know is what is the velocity of this mass. So if I can figure out the voltage difference here, which is U car, for given a value of UR, if I can figure out what is U car, then I have solved the problem. So when you are looking at this circuit, think about it. For very low frequencies, the impedance offered by an inductor is, for all sets of frequencies, is omega L. As frequency is very low, omega is going towards 0, the total impedance offered by an inductor is going towards 0. So for very low frequencies, an inductor behaves like a short circuit, right? As in frequency goes up, omega goes up, and the impedance offered by that inductor, which are these compliance members, this is a compliance member, this, it keeps on going up significantly, and at very high frequencies the impedance offered, it becomes closer and closer to an open circuit. For a capacitor it's just the inverse, because the impedance is 1 over omega L. So at low values of frequencies, it tries to behave more and more like open circuit, and at high values of the same thing, it behaves more and more like
short circuit.
Short circuit.
Sir, in the previous example, we added a current source. Sir, how do we determine the direction of the current? Like, where should it be placed? What is the direction of the current?
You have to assign the direction of the current source in your circuit itself. Like in this case, you assign a positive and negative based on the physics of the problem. You assign a positive voltage and a negative voltage. Similarly, you have to assign the direction of the current in the circuit itself. So it's your understanding of the physics that will help you understand. We will talk a little bit more about this problem, and then we will talk about acoustic elements. So this circuit, here the current can go in this loop, which we call loop 1, and it can also go in this loop, which we call loop 2. And then within this loop, the current can go either through like this, through this branch, or it can go through this branch. So we will very quickly, without doing very elaborate calculations, try to figure out what are the parameters at which these breakpoints happen. What is the breakpoint before which current goes through this branch, and what is the breakpoint after which current goes through this branch, and so on and so forth. So what are the breakpoints? If we are trying to develop a transfer function, which is U car over UR, suppose we are trying to develop this transfer function, and then I develop a board plot for this, then the board plot will have some breakpoints. What are those breakpoints going to be? Today we will just talk about those breakpoints, figure out those breakpoints, and later class we will develop an exact board plot without solving the whole equation. So my first breakpoint is going to be, going to be related to this part, CMS and a mechanical resistance in parallel. So this is my first breakpoint. CMS, RMS. So for very low frequencies, because omega is very low, the impedance offered by this inductor will be low. There will be a point where this impedance due to CM will equal RM, and after a certain set of that frequency, critical frequency, RM will be larger than omega times CM, right. So that is my first breakpoint. So the criteria for that will be omega times CM equals RMS, or omega 1, which is my first breakpoint, is RMS over CM, or F1 equals 1 over 2 pi RM over CM. Now we'll assign some values to these properties. So CMW equals 4 10 to the power of minus 6 meters per Newton. The mass of the wheel is 30 kilograms. CMS, which is the compliance of the spring, is 1.7 times 10 to the power of minus 5 meters per Newton. MMC, which is 1/4 the mass of the car, including the weight of passengers, is, let's say, 455 kgs. These are realistic numbers, so that you get a feel. Did I miss anything? RMS is 7 times 10 to the power of minus 4 meter over Newton second. So I plug RMS and CM, this is CMS. So what I get is F1 is 6.6 hertz. What does that physically mean? That physically what that means is that the influence of this mechanical damper becomes significant only after 6.6 hertz. Before that, this is playing a bigger role. Stiffness, member, is playing a bigger role. So this is my first breakpoint. So this will give you some insight how you design or identify what is the right damping coefficient and the right stiffness for a system which is similar to this circuit. Now the second breakpoint would be, so current is going in this loop, which is loop 2, and before a certain threshold, that is when CMS is significantly important, there will be a resonance point, because CMS and MMC, the impedance offered by these two will be out of phase, because the impedance offered by CMS is j omega times CMS, and the impedance offered by capacitor is 1 over j omega MMC, right. So they are out of phase, but as omega develops, grows, there will be a point when they equal and cancel each other. So my second breakpoint is, so below 6.6 hertz I can neglect this resistance, and I have this circuit in an approximate sense. There will be some current flowing through the resistance also, but in an approximate, very approximate sense, I have CMS and here I have MMC, and the condition for resonance would be 2 pi F2 times CMS equals 1 over 2 pi F2 MMC. So F2, when I solve for it, is 1.8 hertz. So in my board plot, there will be another break at 1.8 hertz. So as I am developing a board plot, which will happen later, I should be aware that I have to do, there will be something special happening at 1.8. And similarly, I have an inductor and a capacitor is in series in loop 1, right. So there will be a breakpoint associated with loop 1 also. So the breakpoint, the third breakpoint is for loop 1. Circuit will be something like this. MMW, CMW, and my breakpoint will be F3. Just as we developed the second breakpoint, it comes to 14.45 Hertz. So this is all we will do today in this class, at least in context of this problem. But we will develop this problem further in some of the subsequent lectures. But bear in mind that what we have done here is we have developed an electrically equivalent circuit. Just by looking at circuit, we were able to figure out what are the different transition points based on visual understanding of the circuit. And then later we will see what is significant about those transition points. And maybe in your, once you go back to your home, you can try to develop it. It would be an informal homework. So now what I will move on to is acoustic circuits. So we have developed electrical networks for mechanical systems. Now we will develop similar network for acoustic systems. In an acoustic circuit is an open tube. So I have a tube which is open at x equals 0, and the tube is L long. My axis for x is going away from the tube. So my boundary condition at x equals 0, as we had talked about earlier also, is that pressure at the exit point is 0, the fluctuation pressure. So my relation for P and U, which are both functions of x and omega, I can write them as P plus, P minus, P plus over Z naught, P minus over Z naught, and then I do E minus j omega x over c, E j omega x over c. And once I impose the boundary condition, I find that P plus equals minus P minus, which we have also seen earlier. In our earlier classes also we have proven. So using this equivalence between P plus and P minus, what we get is P U, again the functions of x and omega. I get P plus minus P plus, P plus over Z naught, and then I get P plus over Z naught. Then I get E minus j omega x over c, E plus j omega x over c. And if I simplify this, then I get minus minus 2j p plus sine omega x over c, and I get plus 2p plus cos omega x over c over z naught. So what we are interested is trying to develop an expression of impedance of the tube at x equals minus L as we are looking into the tube. So the impedance is Z equals T over U, x equals minus L, and when I put x equals minus L in this entire relation, what I get is minus tangent omega x over c times j times z naught. And when I put x equals minus L, I get plus z naught j tangent omega L over c. I'm taking minus sign out, and that eliminates the negative sign.
Maybe plus tangent.
Yes. I'm putting x equals minus L here. So when omega L over c is very significantly smaller than 1, basically what that means is L is significantly smaller than c over omega, or L is significantly smaller than lambda over 2 pi. So for this condition, when L is significantly smaller than 1/6 of lambda, this relation becomes Z equals Z naught j times omega L over c. So we have seen that Z, which is the impedance, is Z naught times j times omega L over c. Now we know that Z naught is rho naught c. So once I introduce this relation in this, I get Z equals j times omega rho naught L. Where rho naught is the density of air, and this is basically T over U. If I equate T such that it is similar to voltage, U is similar to current, then this relationship looks like the relationship for an inductor, because there is a j omega here. If I invert these analogies such that T looks like current, U looks like voltage, which I did in mobility analogy, so in such conditions a closed tube looks like capacitor. So here my thing looks like I have an inductor here of value rho naught L, voltage across the inductor is P, and the current flowing through is U. And in mobility equivalence, I have a small closed tube behaving like a capacitor, rho naught L, voltage across it is Q, and the pressure is. So now we introduce not new term, a term which we have talked about earlier, but we will revisit that, and that is ZA, or acoustic impedance. So again, it could be a function of x and omega, and that is basically, it is a function of pressure, which is again dependent on x and omega, and volume velocity. So this is same as T over U, both are functions of x and omega, times 1 over A, where A is the cross section in this case of the tube. A is the area, cross sectional area of the tube, and this is basically Z x omega divided by area. So the acoustic impedance for an open tube minus L omega at x equals minus L omega is J times omega rho naught L over A. And I can use this acoustic impedance in mobility analogy as a capacitor, and in impedance analogy as an inductor. So now we will talk something called acoustic mass, and we will try to develop some sense of, we will see how acoustic mass behaves like a mass in mechanical area. So we are right now still in doing all these discussions in context of a small tube, open at both ends, and it is small in the sense that its length is significantly less than lambda over 2 pi. Again, you have a small tube whose length is significantly small in this sense. Because it's very small, the pressure, then the air inside that tube, because based on some of the discussions which we have talked about earlier, that when you look at the velocity profile in such a tube, the velocity profile in such a small tube which is open at both ends is such that it does not change significantly as I move on x axis. So the air inside such a tube moves like a rigid mass, it moves back and forth. If I have a pressure here and the tube is extending and it's fairly small in length compared to the overall lambda, then because of that vibrating piston, the air will move more or less like a rigid mass back and forth. So if that is the case, then I can use this relation, force equals mass times du over dt. Well, this Newton's law is applicable to rigid bodies. That's why I am able to use that. Now force is pressure times area. So P times area, where area is the cross section of this tube, is mass, and mass itself is density times the volume of the tube, which is L times A, times du over dt. Now I know that area times u is volume velocity. So I can say P times A equals rho naught L times dVV over dt. Pressure equals rho naught L over A times dVV over. So what this shows is that if a tube is short in length compared to 1/6 of the wavelength, then because the air is more or less behaving in a very rigid way, so it moves back and forth and it is governed by this relation. Now what you have here is dV over dt term. So depending on how you look at it, if you move to a mobility equivalence where Vv corresponds to voltage and your pressure corresponds to current, then a small tube behaves like an acoustic mass. In mechanical mass behaves like a capacitor. Similarly, this acoustic mass behaves like a capacitor, because then what this tells me is that my Vv equals 1 over rho naught L over A times integral of P dt. So this is the equation for a capacitor. So in mobility analogy, for a short tube, P maps to current, then Vv volume velocity maps to voltage, and the capacitance is called acoustic mass, and that is the value for that is 1 over the term itself, yeah, rho naught L over A. So this behaves like capacitance, and the value of this is rho naught L over A. So if I have a short tube and if I am using mobility equivalence, then the total amount of air, all I have to do is it behaves like a mass, but it's acoustic mass, so it's not the physical mass, and the value of that acoustic mass is rho naught L over A. So I can construct a circuit and where I short tubes, and these tubes physically can be fairly long. For instance, at 40 hertz, the length of a short tube will be anything which is less than lambda over 6, right? And the lambda for 40 hertz sound wave will be 340 over 345, 350 over 40, which is a significantly large number. So these are not like micro devices. These can be fairly long. So we talked about a closed tube, an open tube. Now we'll move to a closed tube. So again, I have a tube closed at one end where x equals 0. It is L long. Then based on earlier classes, we had seen that z at minus L is minus z naught j cotangent of omega L over C, and the condition here is P plus equals P minus because of reflection. So again, for small tubes such that omega L over C is very small, that is L is very small compared to lambda over 2 pi, my Z minus L omega is equal to Z naught j times C over omega L. And then when I put Z naught equals rho naught C, then I get this number as, and I bring j in the denominator, what I get is 1 over j omega L over rho naught C square, and my acoustic impedance ZA at minus L omega is basically Z over A, as we saw earlier, is 1 over j omega times LA over rho naught C square. Now L times A is volume, is j omega, so it is volume over rho naught C square. When we look at the physics of this tube, pressure will be, as we saw in earlier lectures, pressure will be maximum here at the closed end. Whenever you have a closed wall, pressure is maximum here, and from here it will start falling as I move away from the tube. But because the tube is not very long, in the context of L being significantly less than lambda over 2, that fall in pressure will not be significant, right? What that means is that I can approximate that pressure is more or less constant in that tube. It will not go to 0 because lambda, because the length of the tube is significantly small compared to the wavelength, 1/6 of the wavelength. So what that also means is that if I have to understand how gas or the fluid is behaving in this, then pressure is not changing significantly, then I should be able to use the gas law, adiabatic gas law, PV to the power of gamma equals constant, and see what it tells us, how the fluid is behaving in this closed tube where pressure is more or less constant. So that is what we will do now. PT, so PT is total pressure, which is P naught atmospheric pressure plus change in pressure P, and VT is again total pressure. And then now I differentiate this in time. So differential of PT in time will be same as dP over dt, because P naught is not changing with time. So I can call it dP over dt times Vt gamma plus Now I differentiate Vt to the power of gamma in time times Vt gamma minus 1 times dVt over dt equals 0. Vt is original volume plus change in volume, which was tau, and the original volume does not change with time. So I can erase this and I can replace it with d. Now d tau over dt equals area of the tube, cross sectional area, times dx over dt equals a u equals volume velocity. So I can replace this whole term by volume velocity in this relation. So we get dp over dt times Vt to the power of gamma plus gamma Pt Pt gamma minus 1 times Vv equals 0. If I solve for dp over dt, I get minus gamma Pt over Vt volume velocity. Now we know that in the realm of acoustics, the fluctuations in pressure are of much lower order of magnitudes than P naught. Similarly, Vt is more or less very closely equal to P naught. So I can simplify this further, minus gamma E naught over P naught times Vv. Again, we know that C square is gamma P naught over, it's P naught over density rho naught. So I get P naught gamma equals C square rho naught. So I put this in this relation, so I get time rate of pressure equals minus C square rho naught over V naught times Vv. The significance of negative sign is, as you have it in a spring, that when you put a pressure, then the volume will reduce and vice versa. So that's significance. So based on that, I can drop my negative sign and I can say volume velocity equals original volume over rho naught C square times dP over dt. What this is showing me is that a closed tube behaves like a spring, and physically it makes sense. If you have a closed volume and you put a pressure on it, it's not behaving like a mass, because mass has nowhere to go. It behaves like a spring, and we had done some earlier some problems also on that. The stiffness of that is this number. This relates to this V naught over rho C square, the acoustic stiffness. The other thing is that as we were developing this relation, we did not use the one-dimensional wave equation very explicitly. We did use, in the case of an open tube, theory of one-dimensional equation. In this case, we had made one single assumption, that the length of the tube is less than lambda over 2 pi. So what that means is that even if I have not necessarily long a tube, but it could be any closed volume, it could be an arbitrary sac like this, as long as the longest dimension of this sac is significantly less than lambda over 2 pi, the volume velocity at the exit point of that here will be related to change in pressure in such a way, and it will behave as a spring, as a mechanical spring. So, in mobility analogy, for a closed sac, Vv again we saw is similar to voltage, pressure corresponds to current, and V naught over rho C square is called acoustic compliance, and this corresponds to inductance, because the relationship exactly, volume velocity is something like L times dP over dt, which is the rate of change of current. So, we have developed equivalence for acoustic mass, acoustic compliance, and now we will go to acoustic resistance, and that is fairly straightforward. So, you can have a screen, a fine mesh. It could be, the screen could be a piece of cloth, or it could be crisscross of wires, and as air flows through it, because of viscosity, it dissipates energy. So, in that case, P, which is function of x and omega over u x and omega, is called Ra. And in mobility analogy, it is 1 over Ra is my acoustic resistance, and that is such that my voltage across this thing is Vv, and the current flowing through this is P. So, this is for mobility. So, we have done all the three elements: resistance, mass, acoustic spring or acoustic compliance, and the last one is a transformer, an acoustic transformer. What could be an acoustic transformer? Basically, what happens in a transformer, electrical transformer? Current goes up, or steps down, right? Voltage steps up or steps down. It has to have a stepped cross section, because the stepping function is, it goes up, it's not gradually going up or gradually going down. So, if I have a tube which has two different cross sections, then that could work as an acoustic transformer. Acoustic transformer. So, a physical device could be like this. So, I have area here A1, here my area is A2, my input parameters are P1 and VV1. So, again, when we are talking about acoustic elements, it is not velocity and pressure, it is volume velocity and pressure, remember that. And here my output parameters are P2 and VV2. So, the equivalence relations between two sections of this tube would be what? For conservation of mass or continuity, I should call it U1, velocity 1 times A1 equals U2 times A2, which gives volume velocity 1 equals volume velocity 2. That is the first equivalence, right? The second equivalence is that P1 equals P2, because at this interface the pressures have to equal. P1 has to equal P2. So my velocity can go up, but the volume velocity will remain same. My pressures will also remain same. So this is a little different than regular tubes where water is flowing, but when we are talking about sound, it's a little different. So what will be the turn ratio in such a transformer? 1:1. Volume velocity 1 is same as volume velocity 2, and P1 is same as P2. The turn ratio is 1:1. So what is changing, step going up or down, is the velocity, but not volume velocity. Volume velocity is present. And finally, so we have developed three elements in the area of acoustics: acoustic mass, acoustic compliance, acoustic resistance. We have a 4-point transformer, and then there are laws of, like Kirchhoff's voltage law and Kirchhoff's current law. Similarly, here you have similar conservation of that. If you have a closed circuit, VV1 plus VV2 plus VV3 equals 0, and then also at a node pressures are flowing, then P1 plus P2 plus P3 and so on and so forth, they also equate to 0. So what we have done in last couple of lectures is we have developed equivalence between electrical, mechanical and acoustic rings. What is missing is that how do you jump from acoustic to mechanical? There is a junction, interface point. So we have not talked about that how do you jump from electrical to mechanical, and how do you jump from mechanical to electrical? Meaning that if you have current coming in, what is the transformation happening that your current transforms to force? What is that relationship? So in the next class we will talk about that.